Okay, students of math. This is the last type of asymptotes that we're going to be looking at. And these are called oblique asymptotes, or sometimes they're called slant asymptotes. And the name kind of says it all. They're basically asymptotes that are not perfectly horizontal or perfectly vertical. You know, they're basically lines that have some kind of a slope to them. So how do we spot when we have these? Okay, well, let me just tell you exactly how you spot them. Remember, we're dealing with rational functions. Okay, so there's a polynomial on the top and a polynomial on the bottom. And each polynomial has a degree, right? So category number one, if the top has a lower degree than the bottom. Okay, so if the polynomial on top has a lower degree, and the top one, and then there's a higher degree on the bottom. So for example, it could be something like x cubed, and this one might be x to the 5. That situation always tells us that we have a horizontal asymptote of y equals 0. Okay, so that's category number one. Then we also looked at, well, what if you have the same degree on the top as you do on the bottom? Same degree, and on the bottom, same degree. And what happens there? Well, that's going to lead you to a situation, for example, something like this, where you examine, oh boy, I've got 3x to the 5th and 6x to the 5th, and you kind of cancel off the these powers of x that dominate, and you go, oh, okay, so it's 1/2, so the horizontal asymptote is y equals 1/2. Okay, so these are two types of horizontal asymptotes that we've looked at. Now, there's one type of situation that I haven't looked at yet, and that is, what if the top is 1 degree higher or 1 degree more than you have on the bottom? So let's just say the bottom is g of x. Now, an example of that might look something like this. Say you looked at your top, and you go, oh, look, 4x to the 7, okay, and then whatever else, maybe minus 10 or something. And then on the bottom we can see, hey, it's a 1 degree less than that. Look, it's 1 degree lower. When you have that situation, this is when we have the slant asymptotes. Okay, so that's how we recognize when they happen. And be advised that these ones can be pretty complicated. They're a little bit more work, so we're probably never going to run into ones with x to the 7 and x to the 6, just because those would be a fair bit to try to graph. So let me go through the process now of how we identify, now that we've identified that we have a slant asymptote, okay, how do we figure out what it is? Okay, let's clear the screen, and I'm going to start by bringing back something you might remember from elementary school. If we look at 14 divided by 5, we can write that as 2 and remainder 4. But there's another way that we can write that. So I say, or we could write it as 5 goes into 14 twice, and then I put the remainder on the top of a fraction with the same divisor on the bottom. So we can write it as 2 and 4/5. Now, what does 2 and 4/5 actually mean? Well, if you think about it, when I said it, 2 and, so 2 plus 4/5 is what that actually means. Now, this might seem like I'm being very, very picky, but it is the key to dealing with finding oblique asymptotes. So what I'm going to do is I'm going to take a function now. So this is going to be my first example. And it's going to be a situation where we recognize, hey, there's an oblique asymptote, and how are we going to figure that thing out? So here's what we got. 2x squared minus 5x plus 7. And that's all going to be over x minus 1. So first things first, I look at it and I realize, oh, that's a second degree polynomial on top. So that's second degree. And then on the bottom, it's x to the 1, which is first degree. So I go, yeah, this is 1 degree higher than the bottom. So that tells me I've got a slant asymptote. Okay. So how do I find it? Well, what we do is we do long division. So the fastest way to do long division here, especially when you've got a nice little binomial here that you're using as a divisor, is to use synthetic division. So that's the fastest way to do this. I'm dividing by x minus 1, so I'm going to plug in a positive 1, right? That's the number that turns this into 0. And the coefficients of my of the top function are 2, negative 5, and 7. So I bring that 2 down and then use my synthetic division. So 2 times 1 is 2, and add them up. Negative 3 times 1 is negative 3, and add them up. So I got 4. Now, what is this actually saying the answer is? Now remember, use this as a guide. Here we took the answer, which was 2, and then there was the remainder, and then I processed it a little differently. So let's do that here. So my answer is 2x minus 3, and then I have this remainder of 4. So now I'm going to process that a little differently, just like I did over here. What it's saying is I have 2x minus 3, okay, that's kind of like the 2. And then I'm going to add to that, so I'm going to build a fraction with this remainder. So I'm going to put the 4 on top, and the thing I'm dividing by underneath it. Okay, so this, now this might look a little strange to you, but that's exactly what we did over here, right? We're dividing by 5, so I put 5 on the bottom. And here I was dividing, whoops, there it is, dividing by x minus 1, so I have x minus 1 on the bottom. Here we put a 4 on the top because that was the remainder. Well, we had a remainder of 4, so we put the 4 on top. So that's how I build this fraction. And then this is just my quotient. This is my answer. You know, when I divided 5 into 14, it went twice. So that was my answer, 2. And here, when I divided this top polynomial by x minus 1, well, my answer turned out to be 2x minus 3. And, you know, that was my answer. So this is no different, even though it looks more complicated. Now, what I'm going to do to figure out basically what the slant asymptote is I have to ask myself, asymptotes occur as x gets bigger. Okay, so as x gets bigger, what is happening with this thing here, with this answer? Well, 2 times x is going to get really big, minus 3, and then plus this. Now, what happens here as x becomes a bigger and bigger number? This is going to be like 4 over a million minus 1, and then it's going to be 4 over a billion minus 1, and so on and so forth. So in other words, this guy here is going to turn effectively so small that we're going to say it's too tiny to even worry about, and really this is what happens to the function as x becomes really big. This is our function. We can ignore this guy and just say, aha, that's the function. As x gets big, or similarly, or as x gets small if you're heading off in the negative direction. What's happening is the function itself is really behaving just like this. It's behaving like y equals 2x minus 3 because this part of the function can be, ignored because it gets so small. And so what we have here is this is the equation of the oblique asymptote. So we did it. That's how you find it. So that's where I'm going to stop, and I'm going to come back, and we're going to look at other examples because it is quite a process.